let's start. It's a great honor to be here and sharing this talk with you. So the session I will talk today is about the flaws and vulnerabilities in system UI and the system server, and how to be using the bugs and the vulnerabilities to bypass the restrictions to achieving hijacked attacks on high-version Android platform. So simply introduce myself. My name is Wei Min Cheng. I'm a security researcher at Qianxin Tiangong Lab. I focus on mobile and AOSP security researching. Really is our group's leader, helps a lot when I'm doing this research. So agenda contains 4 different parts. The first part, I will introduce what is activity hijack attack, also called AHA, and how AHA work on old version Android platform. And next, I will introduce the security policies and restrictions released by Google this year, and how these policies make AHA not work. The next part, I will bypass these restrictions by finding some new attack surface and vulnerabilities. And in the end, I will combine all the bypass techniques to weaponize the fortune, and then we'll have a video demo for this. So about the AHA, it is an old and traditional attack scheme, and many malware such as adware, ransomware, bankbot, likely to be using this technique to injecting evil content to trusted application. Then they can perform hijack to stealing sensitive user data or dangerous runtime permission. That is what AHA can do, and the hijack happens. Users usually don't know they're under attack. We take a real world, we take Android 4 as a sample, and you can see code snip in the screen. It is belong to a real world malware, real world ransomware SIM blocker. And you can see the SIM blocker creates a schedule, and the schedule checks the topic activity per second. If the topic activity is not the ransomware itself, it will start activity with a special flag, the new task flag to seize the foreground. After seize the foreground, the malware can push the previous application text into the background task. Now malware can forge the identity of trusted application. It's kind of like a Strandhawk attack scheme. But why malware have to seize the foreground to perform a hijack attack? Before we talk about this, we need to know something about the text and the backstack. And from the described in the developer document, the text stack is a collection of activities. And used in the system, usually separate the text into 2 types: it's foreground text and the background text. And user in most cases can only interact with only one foreground text, such as you are using application 1, and at this time you can interact the topic activity of the application 1 foreground task, but at the same time you cannot, you are unable to interact with other application in the background. So that is why the malware have to seize the foreground to injecting evil content to the screen. After understanding the related knowledge, now we can simulating a hijack attack. We simulate there is a user device, and the user has installed a payment application eBank in his device, and the malware in background is keep leaking the runtime state of all proxies. At this time, eBank user click eBank, the system should blow the eBank to user's face. And also at the same time, the malware in background detect the eBank comes to foreground, then injecting a fake eBank login page and seize the foreground. And it is a low-cost, high-return attack scheme, and in all the Android devices, it affects almost all applications. So we can conclude 3 key factors of HA: the ability to start activity from background, detecting runtime state from background, and run in background persistently. Lose one of these factors, we cannot achieving precise hijack attack. Of course, Google will not let this attack happen. So this year, Google released a series of security policies and restrictions. The first restriction is about the runtime state leaking. Before API 22, malware can leak the runtime state of other application directly by calling some special interface. And you can see the poke code in the screen, and it gets all running tasks and all running proxies directly and without any permission. But after API 22, this special interface can only return call state. But for API 26, malware still have chance to bypass these restrictions in a side-channel way. Proxies can access the proc folder of other proxies directly and request no privilege. So malware can detecting the targets where the targets come to foreground by access its OOM-ADJ score. In 2017, Google updated the SELinux policy. The policy added two new line code. The new line code restricted the application to access file in non-app domain. It's kind of like a PID2 protection. So malware from now cannot access the OOM-ADJ score from of other proxies. But that's okay, we still have a compromise scheme. We take a real-world malware mystery bot as an example. It tends to use usage state manager to leak the runtime state indirectly. But the list components request dangerous runtime permission and request complex user interaction, such as guide user into the setting app and guide them to switch on options manually. And in some third-party ROM, the phone will pop out a full screen to one user when granting such a permission. The second restriction is about the BAL. After API 29, application without privilege can start activity from background. And no BAL means our malware cannot injecting the screen from background, and the malware have to detecting the runtime state from background. So due to this restriction, many malware and hijackware disappeared. So the compromise is tend to use accessibility services or other system services, or we can use the system alert window permission to overlay the screen. But all these request a complex user interaction and the dangerous runtime permission. And the second scheme is we try to satisfy the BAL restriction exceptions in the developer document. But all these restrictions, such as request bound by system or request hold system privilege, is almost impossible to meet. The third restriction is about the background execution limits and LMKD. After API 26, background services cannot run in background precisely, and it will get the high out-of-memory ADJ score, and this high score means low priority. And these services will be considered as background proxies by system. And the idle proxies will be killed by LMKD first to release memory. And after API 24, system broadcast trick also get banned. This means malware cannot pull themselves up by listening to the broadcast trick. A compromise scheme is provided by Google. Google addressed the developer to start the foreground services for get a low OOM-ADJ score. But the foreground services need to continuously notify user, and it cannot run in background silently. Assuming we all use compromise scheme, which means malware have to grant dangerous runtime permission and request complex user interaction, it even cannot run in background silently, then it means the attack will be detected by user. Even we start foreground we take a Xiaomi OS as an example. When user clear the recent task from background, Xiaomi will directly call force stop to all proxies, which means our foreground services even will get killed. So in this talk, what we need to do is bypass all the restriction, achieving undetectable and no permission required hijack attack. So the first hurdle we have to face is about the BAL restriction. This is the most important part of the flow chain. When malware start activity from its app domain, the request will be handled by activity manager services. Then the system will go to the execute request function, and you can see code snip in the screen. The function calls should the background activity start, then returns the result to restricted the BG activity member. Next, system will try to start target component, and in initial state function, the code will decide whether make the application come to foreground by check the restricted BG activity, And you can see if the await move to front member is set to true, then in the start activity inner function, the move to front function will never be called. So we still need to focus on the check function and find ways to bypass it. And the developer document gives some exceptions for the check function, such as if an application has a visible window, it can start activity from background. The simplest example is to make an application come to foreground, and this task will be considered as visible by system. But we do not consider this. We back to the check function. And the check function call has active visible window function and return a result to the system. If the result is true, the check function will return false for telling system do not prevent this application come to foreground. Then next, the check function will call has active visible window. Inside the code, you can see the code get the core UID and try to access its window type. If its window type is bigger than the first system window value, this window will be considered as visible by system. And the window type is related with its z-index. We take add window function as an example. Before system call add window, it will check the base layer between new window and the existing window. If the base layer, you can see the base layer member is higher and its z-index will be higher. And you can see the base layer is related with the get window layer from type. So now we can know the window type is bigger, the z-index will be also bigger. So the check function requests us to get the system window, and the system window and our non-privileged application are able to get a system window, and usually it get a base application type window. It is a low z-index and invisible in most time. If we want to get the system window, we have to request the system allowed window permission. It is request complex user interaction. So the picture-in-picture feature is belong to Android system and also called pipe mode. It is a compromise scheme Google provided for developers. Any application without the source permission can start and can get a system floor window at any time and pin its activity to a small pipe window at the top of the screen. And the pipe window is handled by system UI, and of course its window type is bigger than first system window value, and the request no permission. Of course, it is a good attack service. We take video app as an example. You can see the app comes to background, goes to background, but it goes to pipe mode and pin its activity in a small pipe window. So the system will consider is in visible state because its window type is system and it's in pin mode. But we still cannot abuse pipe directly because pipe window can't hide from screen. And even we use the transparent theme in the pinned activity, the system UI will make the pipe window visible for user. And the user can remove the pipe window at any time. So pipe is a highly detectable feature. But the pipe still have a history bug. We can set abnormal hit and weight in activity. Then the system will input the abnormal 1 pixel object to pipe window. Then you can see the screen. There is a very small dot. That is abnormal pipe, only for 1 pixel. But it is invisible and untouchable for user. But interesting is it is visible for system. So the patch is quite simple. You can see the pipe bonds algorithm component. It has some checks to check whether the passed in value is abnormal. If it is abnormal, it will only return the fixed value. So it is a nice bug to expanding attack surface. Now we no need to bypass window visible check because we can find a way to abuse pipe, such as create a legal system window, but this window are user undetectable. Before we finding vulnerabilities in pipe, we need to know how pipe work. And the app called interpipe mode, and the system ATMS will handle this. Then the system will go to move activity to pin the root task function. And in this function, you can see the code called set window mode and the pin and the set the text in pin mode, and the len called set default text appear. And inside the code, it will IPC with the system UI side. And the system UI side on takes appear, the callback function will be triggered, and inside this code, the system will init some pipe params such as set up animation transition and set up window size. Anyway, pipe will be officially rendered here. So we can now complete the pipe startup chain here, and we can get a simple sequence diagram. If we want to take pipe, we need to take the weakest part in this chain. So our first scheme is try to prevent IPC. You can know, we said before, the ATMS will set the pin mode. And after set the pin mode, the system will consider it as visible. Then if we block IPC here, the system UI will not render the pipe window. Maybe we can get undetectable, but still impede the state task. But unfortunately, in user space, we almost had no way to affect the code execution in system server. So the second scheme is try to tackle the system UI side, like creating an abnormal window type. The set resource reactor hint is an interesting interface. It can auto-scale and crop the activity window to a defined size by passed in reactor object. So if we input a abnormal reactor object, where we'll get a abnormal pipe window. Here we write the poke, and the poke run in Android setting, and of course it get a 1 pixel it get a 1 pixel window by the passed in 1 pixel rect object, but after half seconds it come back to the normal size. So what happens inside the half seconds, and any ways to expanding the duration? So we need to trace the rect object, and inside the onText appear the callback function, and we can know the rect object pass to the schedule animator resize pipe. And then inside the code, the code set up a transition and set the duration. This duration is a fixed value defined by system. It's 425. And after some debugging, we can know this transition will resize the pipe window into the rect object defined size. So what happened if after the resize? Then this transition object will set up a callback handler. This callback handler rewrite the on-pipe animated animation and the interface. Then it will be called after the pipe animated played over. Within the code, it will call the finish resize. Finish resize will create the window container transition object, also called WCT. It will be passed to the prepare finish resize transition with a normal size rect object defined by system. And then it will set the surface control transition and the system defined rect to WCT. Then system will carry WCT to IPC with system. Before IPC, the system UI side will extract the SCT from the WCT, then carry this SCT to IPC. Then the system side will go to set main window side transition. In this transition, the system will directly call merge operate to rendering the SCT on the screen. This operate will cause pipe window resize to normal size. And now our target is try to prevent the merge. The first thing we want to try to prevent IPC, but not work. So we compare the main branch of this function, and we found the API 32 has a code change. And from its commit detail, we can know it is a functional patch instead of a security patch, so it is still valuable to analyze API 32. And 32 do not call merge operate. And instead call merge is set the SCT to a global member. And this global member and we follow the global member, we can find the set the surface boundaries locked function will get the SCT. So we hook this function find what happens in this call chain. We find the familiar function prepare surface of this function is belong to activity record components. This component is related with activity launch and the rendering. So this means we can indirectly control this call chain from in the user space. Now we know API 32 and 33 will finally goes to the set main window side transition function, and we know the 33. This function will call merge, and we almost have no way to prevent the pipe resize to normal because the chain is handled by system UI. But in 32, this function will set the SCT to global member. Then inside the activity redraw operate, this operator will start up a chain and access this SCT. And then the code will call merge. So if we frozen the redraw operate, well, maybe the merge operator will not be called. So we get our first CVE. You can see there is very small dot in the screen. It is user undetectable and invisible. This pipe can keep staying in the screen in the phone, and because we force the UI third. But this is still API 32 bypass. We want a bypass after API 33. So we look into the API div list. We found the new text surface. The function make launch into pipe. This function will return activity options object. This object you can think it as additional options for activity launch. Then inside the code, the function will save the received pipe to package the bundle object by a specific key. The key name is launched into pipe params. Then the packaged bundle can be used to set options for activity start. We trace the bundle object inside the activity launch chain, and you can see the bundle will finally be passed to a function start activity inner. And about this function, we have analyzed it before. It will call move to front if the application pass the BALO restriction check. So what will the bundle object do inside the code? So inside the code, you can see the code call is launched into pipe to check the bundle if the bundle takes the specific key. And after the check, you can see the code directly call move activity to pin the root task without any other check and no BAL restriction check. So which means our malware can start the activity from background at any time and start activity into pipe mode. So we get our new CVE for after API 33. So the second high we'll have to face is about the state breaking state. After bypass the BAL, we have to do this. This is the bug I meet when I'm doing developing. You can see the slot exception in the string. The exception happens when I merge the code. After merge the code, the system tells me I try to start services from background. But before I merge code, I use in the bug position I use bind services. After merge, I use start services. After checking the developing document, we can know bind services is not under limit of the background execution limitation. So that's why app crashed. And we can know background execution limitation well through exception when app try to start background services. In this case, we can abuse this limitation to be a background proxy detector by targets exported services components. So you can see I write a poke code to start the targets from background, and if the target is in background, the system side will return an abnormal component's name. This abnormal components will cause the user space through the exception, which means I can catch this exception in user space. So I can detecting targets come to foreground by a second away. And this issue is still waiting for CVE. And due to time reason, other tricks, please see my white paper. Next, we will break the LMKD, achieving persistently proxies in background. Before we talk about LMKD, we need to know something about the out-of-memory ADJ score. You can see if we get the higher score, means our proxies will have a lower priority. And you can see the screen. Our shell keep checking the background. Keep checking background proxies, and this background proxies, its priority is lower and lower, and in the end, it gets killed by LMKD. But we can start foreground services, and this foreground services usually get 200 score. It's a high priority. But we said before, it is no way to run in background silently. By analyzing the code of calculating the priority in system, we can know if the proxy services is bound by third party and the third party priority is higher than self. Code will check whether the client priority is higher than the visible application ADJ value. If true, the app can get a visible app priority. So is there any way to be bound by system proxies? Before we know this, we need to know something about the managers. There is several managers in frameworks such as activity managers, window managers, and package managers. And the non-priority application can operate managers by correspond iBundle object. And the managers usually run as a system user. So can we abuse managers? We take accessibility services as an example. The accessibility feature is handled by accessibility manager services, and the non-priority application needs to declare specific internal filter before use this feature. And this filter is pointing to a specific application services component. Accessibility manager services will first find all application wants to access this feature by the internal filter. Then it will create a connection objects inside the code, and this object targets this application. Then code will call bind locked function to bind into the app. One poke, now we get the high priority proxies because it's bound by system proxies. But this accessibility feature is request dangerous runtime permission, so we do not use this to achieving persistently proxies. We found another manager called the account manager. This is API added from API 5. It's 2009, and this is a manager used to measure. This is a manager used to measure the device account by at the same time, to use these components, non-priority application also need to declare specific internal filter. The key point is to use these components, we do not need to request a dangerous runtime permission. So we have a chance to call add_count interface by this manager. The system will create the system objects targets this core application. Then system will call the bind function of this system object. It will make the system bind to our poke code. And our poke will get the high priority and the user undetectable. And there's some more tricks can make account manager keep binding to non-privileged application, that the proxies are unkillable. Due to the time reason, we do not talk about this, and this trick can be found in my white paper. And this is a code, video demo for persistently poke. First, we check the Android version. It's API 34. We start poke start running, and we make this application comes to background. We try to check its out of memory ATJ score. It's a high priority. We try to force stop this application, but you can see the poke is still running. It can be killed by any operator, even we call force stop. We still check its out of memory ATJ. High priority. Then we try to kill it in ADB shell. Before stop it. Still running. So next is the full chain of hijack exploit. Check the Android version, it's 14. We need to hijack all these 3 applications. We first run this application to make sure this app runs normally. Then we start poke. We click hijack all. It starts detecting the runtime state. After we click it, we get hijacked. YouTuber also get hijacked. Telegram is also get hijacked. So this is the end. Thank you.